sklearnsvmSVR. Description: the support vector regression SVR model in scikit-learn sklearn is a powerful technique for regression tasks, aiming to find the best fit line or hyperplane that minimizes the errors between predicted and actual values while considering a margin of tolerance epsilon. It utilizes the concept of support vectors, which are the data points closest to the decision boundary, to define the model. Inputs: X. The input features, typically a 2D array with each row representing a sample and each column representing a feature. Y. The target values, a 1D array corresponding to the output values for each sample in X. Outputs: model. A fitted SVR model, containing the learned parameters. Predictions: the predicted values for new input data, generated by the trained model. Steps: data preparation. The input data X is pre-processed, which may involve scaling, normalization, or feature engineering to improve model performance. Model initialization. An SVR model is instantiated with specified parameters, such as the kernel function, regularization parameter C, epsilon, and others. Model training. The SVR model is trained using the provided input features X and target values Y. This involves finding the optimal hyperplane and support vectors. Prediction: the trained SVR model is used to make predictions on new data. The model calculates the distance of new input points from the decision boundary and estimates the corresponding output values. Metrics: mean squared error. MSE measures the average squared difference between predicted and actual values. Root mean squared error. RMSE the square root of MSE, providing a more interpretable measure of error in the same units as the target variable. R squared. R2 represents the proportion of variance in the target variable explained by the model. Higher values indicate a better fit. Mean absolute error may measures the average absolute difference between predicted and actual values. Visualization plots. Scatter plot visualizes the relationship between the input features and target values, with the predicted values overlaid for comparison. Residual plot shows the difference between predicted and actual values, helping to assess model bias and identify potential outliers. Learning curve plots. The model's performance on training and validation sets is a function of training data size, helping to identify overfitting or underfitting. Fine-tune parameters. Kernel defines the function used to map data to a higher dimensional space. Common options include linear, RBF, poly, and sigmoid. See regularization parameter that controls the trade-off between fitting the training data and preventing overfitting. Higher values prioritize fitting the data, while lower values encourage smoother models. Epsilon tolerance margin around the decision boundary. Data points within the epsilon margin are considered correctly predicted, regardless of the actual distance. Gamma specifies the influence of a single training example. Higher values indicate a larger influence, potentially leading to overfitting. Uncertainty methods. Confidence intervals provide a range of likely values for predictions, based on the model's uncertainty. Challenges and fixes. Challenge 1: overfitting. Sample use case that resulted in challenge 1 using a complex kernel function or a large C value can lead to overfitting, resulting in poor generalization performance on unseen data. Fixes to challenge 1: use a simpler kernel function, e.g., linear, reduce the C value, or consider techniques like cross-validation to prevent overfitting. Challenge 2: underfitting. Sample use case that resulted in challenge 2 using a linear kernel or a very low C value might result in underfitting, where the model fails to capture the underlying patterns in the data. Fixes to challenge 2. Try a nonlinear kernel function. Increase the C value. Or consider adding more features to the dataset. Challenge 3. Scaling of features. Sample use case that resulted in challenge 3 when features have different scales. The model might be biased towards features with larger ranges. Fixes to challenge 3. Scale the features using techniques like standardization or normalization. Before training the model. Challenge 4. Choice of kernel function. Sample use case that resulted in challenge 4. Selecting an inappropriate kernel function can lead to poor performance. Fixes to challenge 4. Experiment with different kernel functions and choose the one that performs best on the validation set. Challenge 5. Handling outliers. Sample use case that resulted in challenge 5. Outliers can significantly affect the model's performance by pulling the decision boundary towards them. Fixes to challenge 5. Pre-process the data to remove or handle outliers. Or consider robust regression techniques that are less sensitive to outliers.